Hello everyone, my name is Martin Strässer from the University of Würzburg, and I'm happy to present you our paper for the ICPE 2022, which is named Why is it not solved yet? Challenges for production-ready autoscaling. This work has been conducted together with some colleagues of mine from the University of Würzburg, namely Johannes Grohmann, Simon Eismann, André Bauer, and Samuel Kunev, as well as with Joachim from Christowski from the Dativ EG from Nuremberg, Germany. We all know that autoscaling is concerned with the dynamic provision of computing resources under varying load. It is a high-value task in many production cloud systems, as it affects both operating costs and customer experience. Moreover, autoscaling is relevant for several subdomains of cloud computing and is present in traditional clouds, but also in fog computing and serverless computing. When we look into state-of-the-art autoscaling, we see a huge difference in what is present in academia and in practice. In research papers, many different approaches from machine learning, queuing theory, time series analysis, control theory, fuzzy methods, reinforcement learning, and more exist. However, in practice, only a small number of, let's say, advanced approaches are really in use. Many cloud applications are operated with rather simple autoscaling mechanisms. Here, for example, we see a configuration of a Google Cloud CPU-based autoscaler. We see that it has a simple utilization threshold here of 60% and a cooldown period setting here set to 90 seconds. Another example is the default scaling formula used in Kubernetes horizontal pod autoscaling. Here we simply assume a linear relationship between a scaling metric and the desired number of replicas. This can be, of course, in some cases be, let's say, a good enough approximation, but this does not hold obviously for the majority of applications. In our study, we want to assess why there is this significant gap between what is proposed in research in terms of autoscaling on the one hand, and what's really in use in practice on the other hand. Therefore, we first conduct an experimental study with a realistic hardware and software stack, which mirrors the environment present at our industrial partner. In our experiments, we showcase limitations of classical threshold-based autoscalers and show how overloaded services can influence the scaling behavior. Moreover, we conduct some preliminary studies with autoscalers that use uncommon scaling metrics for their scaling decisions. In the second part of the paper, we state 6 core challenges for autoscalers in production systems. These challenges are generic and not bound to specific contexts or environments. That's why they can be used as possible future research directions. In the third part of the paper, we then analyze how recent literature addresses the stated challenges. We also state common assumptions and shortcomings which limit the practical usage of many proposed research autoscalers. The first challenge we state for production-ready autoscalers is balancing proactive and reactive scaling. When we look how autoscaling evolved from its beginning, we see that it started with reactive scaling, which basically relies on system monitoring, and we then react to the current values of our system that we measure. By design, reactive autoscalers rely heavily on the input parameters of the current measurements and also on the configurations that we gave them. Moreover, reactive scaling to some extent need also some SLO violations. So basically some high load and maybe bad response times must occur for the autoscaler that it can react to it and possibly scale up. These obvious limitations then led to the research direction of proactive scaling. In general, we would always scale proactively because we want to match our resource demand in advance. But normally we can't do this because we have only a limited prediction accuracy. Although trends, seasonalities, and so on might be present in our systems, there might be some singular events or anomalies which we cannot predict. And that's why we also need the combination of both. Another thing, or another really challenging thing for proactive scaling are frequent application updates. For example, in DevOps context, when we regularly update our application, we can only limited use the knowledge of the past to predict the future. And that's why this is really also challenging for proactive scaling. As said before, we therefore need a combination of both reactive and proactive scaling, which is named hybrid scaling. Here we combine the advantages of both, but however, there's still questions how or who do we trust which autoscaler in which situation. And this is still an active field of research. This first challenge of balancing proactive and reactive scaling can be really nicely shown on a simple example problem. Let's say we observe unexpected high loads in our system. The question, how should we scale in such cases, is not really easy to answer. Predictive scaling might interpret this as a short-term event, because we basically didn't see the high loads coming, so we think they won't be in our system for a long time. So here on the visualization, they might think about the red cores, basically. Reactive scaling, on the other hand, might suggest a strong reaction, because we observe SLO violations or high response times, and it suggests basically upscaling, because that's pretty much how reactive scalers are designed. So there we see that there's a conflict potentially between these two scaling approaches. In a recent literature, we observed that less than 15% of the papers surveyed in this publication here targeted hybrid scaling explicitly. These hybrid scalers then basically work on real hard rules, how this interaction between proactive and reactive scalers should work. Most papers use reactive scalers only for upscaling and only in the presence of SLO violations. The second challenge for production-ready autoscaling is combining application-specific and generic platform metrics. Hardware metrics, like commonly used CPU utilization or memory utilization, are limited by their design because they have a restricted range of values they can take, normally between 0 and 1. And as shown in previous research, they cannot always be used to derive the resource demand of a specific service. Modern microservices expose many application-specific metrics, which can be used also for scaling. In our experimental study, we focused on Spring microservices, and each of these microservices expose 62 application metrics. We observed that all of these metrics have different characteristics. There are also some in there which are constant through our experiments, so do not have any usable value. However, some metrics are really useful for scaling, and I want to show you this with an example figure and a pretty simple test. In this test, we observe how application metrics behave with an increasing load intensity. We stressed one of our test microservices with an increasing load intensity. In this figure, the load intensity is shown with the brown curve. So we start with a really low load and then end up with a really high load. We stop the experiment when the first request times out, so the service is basically overloaded. In order to show now other application-specific metrics in one figure, we normalized our values. The value of 0 still means 0, but the value of 1 reflects the observed maximum. We see, for example, here that the CPU with the red cores follows the workload nicely. So when the workload increases, the CPU utilization increases as well. This is not really surprising, obviously, but we can also see some useful information in other application-specific metrics. For example, the thread ratio here with the pink curve depicts some kind of early warning for the decreasing service capacity. So it reaches its maximum value some good time before the actual problems occur, so before the first request times out. That's why we can use it as an early warning that our service might be overloaded in the near future. We can also see other metrics, for example, the scrape duration. The scrape duration is basically the time which takes to basically grab the monitoring values from our service. And we see that this metric depicted here with the green cores really clearly reflects evolving or existing problems. So we see that for most of the experiment time, this value is really low. But when the first request times out, this value increases sharply and therefore can really nicely reflect that a problem exists within our application. In contrast to this, for example, when we look at the CPU is right more noisy because we see that the maximum value here, for example, for the CPU has been reached far before actual problems happen in the system. And when the first request times out, the CPU is not at its maximum value. This problem of combining application-specific and generic platform metrics is not really targeted in the recent literature. Most papers only focus on CPU, memory, and response times. There are also some papers out there which use already application-specific metrics. For example, here 2 references which use the number of active sessions or connections in order to scale the application. Our third challenge for the production-ready autoscalers is keeping the configuration overhead as small as possible. As we saw earlier, the performance of autoscalers depend heavily on their configuration. An optimal configuration for an autoscaler might be dependent on the service. For example, let's consider a microservice application with hundreds of microservices. Each of those services have a specific performance profile and also another optimal configuration for autoscaling. Moreover, the optimal configuration might be dynamic, so not static in time. For example, when we update our services frequently, as it takes place in modern DevOps contexts, also the performance profile changes and therefore the configuration of the autoscaler might change as well. Another thing to consider for the configuration is the weight we put on costs against our SLO violations. In some use cases, it might be acceptable that we, let's say, allow 5% of the requests to have a higher response time. In other use cases, this might be totally unacceptable and we would rather go for higher costs instead to prevent such behavior. Another thing for the optimal configuration is that it's always hard to determine, both for application developers, as they are normally not really concerned with the performance of the application and how it behaves in terms of autoscaling. And also, it's hard to determine for the cloud operators or providers, as they might have not full insight into the source code and white box behavior of the application. In the recent literature, this aspect of configurability is only rarely addressed. Normally, research autoscalers require model parameters or thresholds to be set in advance. One investigated approach to reduce this configuration overhead and to explore the configuration space some kind of autonomously is reinforcement learning. However, reinforcement learning requires also the definition of a suitable reward function, which is not always easily in every context, and it requires some significant amount of training data and learning time. The next challenge we address is that scaling metrics might be unavailable, incomplete, inaccurate, or delayed in production systems. In general, we cannot always trust the value of our input metrics for the autoscalers. For this, many related challenges evolved. For example, these application metrics that we showed earlier in the presentation might be unavailable due to overloaded services. And this is dramatically because this is the exact time where we need a scaling decision. And if our metrics are then unavailable or incomplete, we cannot come to a valid scaling decision. Another challenge is that the services are normally dependent on each other. For example, if we might scale up some backend services, we maybe shift the bottleneck to the front end, because now our backend can handle more requests and the front end then may become the new bottleneck. Another thing that we observe also in the literature is that many papers rely on response time measurements. And also in our experimental study, we show that response time measurements can be misleading, especially in high load scenarios. Per definition, the response time always reflects a past state of the application, because it's basically measured after the request left the system. So the request has been processed in the past. And we also show that the response time is not always suitable as the only measure of quality, because some services might throw, let's say, internal errors or unhealthy response codes when they are overloaded. In these cases, the response time might be not the best measure because it can even reduce when errors happen. In this figure here we see a pretty comprehensive example of this challenge. Here we see some measurements that we conducted in order to create our paper, and we see that we here measure the response time of different endpoints for our microservices, and we see that we have for about 20 minutes missing data in our measurements, and we also have incomplete data because the violet curve basically depicts the response time of some requests, but these requests cannot be matched to a specific endpoint, and that's why we cannot really get the full information out of these data. I now want to state the remaining two challenges only shortly. Our challenge number 5 is combining autoscaling, load balancing, and resilience mechanisms. Modern container clouds normally use cloud management or container orchestration tools like Kubernetes, which fulfill multiple tasks, for example, health monitoring, load balancing, and so on. And all these tasks basically run in parallel to autoscaling and influence the application performance and therefore also the autoscaling behavior. In our study, we explicitly discuss, for example, restarts in terms of health monitoring, so the container orchestration tool observes that a service instance is unhealthy and restarts it. And we see that it has significant influence on the autoscaling as well. Moreover, we see an increasing adoption of resilience mechanisms like circuit breakers, which have come into play with the modern microservice architectures, and they also influence the resource demand of specific service instances. In the literature, we see that only few studies combine load balancing and autoscaling and other relevant mechanisms. Our last and sixth challenge is then keeping autoscalers explainable. You might probably also thought that already, that a significant complexity is needed to meet all those previous stated challenges. But in practice, and to also increase the trust in autoscalers, transparent decisions are necessary. So in optimal case, the autoscaler does not only come to really good scaling decisions, but it also can explain why and what factors influence its decision. That was it with our challenges for production-ready autoscaling. I now want to conclude this presentation and summarize our paper. As said earlier, we have the three parts. We conducted an experimental study with a realistic hardware and software stack and motivate some new research directions for autoscaling. We defined 6 core challenges for production-ready autoscalers. We evaluated how the recent literature addressed these challenges in their papers. And we also want to motivate a call for action. So we definitely encourage a closer cooperation between academia and industry in the field of autoscaling. For example, the industry might provide more realistic workload traces, more example services, example cloud services, more realistic hardware and software stacks. And academia should increase the focus on the needs in production systems and on our stated challenges. And we also encourage a realistic evaluation of approaches and would definitely consider to not only simulate the autoscaling, because as we have seen, there might be a lot of challenges present in reality which can be not really assessed within a simulation. Overall, the goal of our paper is to inspire future autoscaling research and increase the use of research autoscalers in practice. Thank you very much for your attention. And if you are interested in our work, join the discussion at ICPE 2022. We are in session 3, Empirical Studies of Performance, taking place on Tuesday, April 12th on 2:45 p.m. Central European Time or 8:45 Eastern Time. And if you cannot be there, feel free to write us an email or find us on Twitter, LinkedIn, or whatever, and reach out to us. And we are really interested in cooperations and in your opinion. Thanks very much, and see you next time.